Hello, everyone. Thank you for joining. We'll be starting shortly, but meanwhile, kindly confirm if I'm audible and you're able to hear me. Awesome. We'll be starting in 2 minutes. All right, I believe we can start. So, hello everyone, and welcome to AI Harness Design Memory Driven Agents. Today, we're going to explore how AI agents can move beyond simple prompts and start using structured memory. Today, we're going to explore how AI agents can move beyond simple prompts and start using structured memory through knowledge graphs. So instead of us treating the model as something that only answers one task at a time, we're going to look at how we can design a system around it, basically a harness that helps it retrieve context, remember decisions, follow constraints, and basically use all of the right tools. So we're going to connect the idea of agentic AI with knowledge graphs, and then we'll move into a hands-on example using Neo4j to see how memory can actually be structured and queried. So before we kick off, I'm just gonna go ahead and just for those of you that are new here, welcome. And for those of you that are familiar with Code Sarah and our sessions and talks and webinars, um, I'm gonna go ahead and introduce myself. So hello everyone, I'm Sarah. I'm an AI and a software engineer. I'm as well into academia and research as well. So I also work as an independent researcher. I have over 3 years of experience in the industry, everything about AI systems, knowledge graphs, ontology engineering, agentic AI, and memory systems. Other than that, I'm also an instructor and I've been teaching since I was 19. Fun fact. My first talk and my first course was when I was 19. Over the last recent years, I've also taught at RHU University. On the side, I'm also the founder of Code Desera and I'm an organizer at GDG Coast Lebanon. A bit about my academic background: I have a master's degree in computer science, another one in data intelligence and AI, and just recently, last summer, I did a machine learning summer school at Oxford. But I'm also just a girl, so I'm a woman in STEAM advocate. For those of you not familiar, STEAM is basically just STEM, but like add arts into it. I'm high on creativity and impact and such. I'm hoping there is some girls joining us here today. So let us kick off with a very light icebreaker. So, how many of you use AI coding assistants daily? Feel free to drop in your answers in the YouTube chat box. I believe the majority is now abusing AI coding assistant tools and such. We have Claude, we have Cursor, we have Warp, we have a lot of tools recently. So I'm sure everyone is currently abusing them. Yeah, a lot of people. All right. Now, What was the weirdest thing that happened while you were vibe coding? I've actually heard a lot of fun stories here. I'm gonna go ahead and share an example. So, this is me chilling after I have deleted the entire code base. I mean, we've all been there for sure. Feel free to drop in your crazy stories in the chat box. Now, here is another fun story. Once I recall, I was working on a research paper, and I had to vibe code some stuff and such. I was doing some data visualizations and such. So apparently, my entire visualizations were entirely built on a fake data set, even though I had the real data set and all. But for some reason, I was using Warp at that time. It decided to fabricate data and hallucinate data and, basically run the code on those basically fake uh, data set, synthetic garbage, basically. So, yep, we've all been there for sure. Now, we're gonna dive into the 5 different levels of vibe coding. I'm pretty sure everyone by now has basically somehow established his or her own style when it comes to vibe coding. So, yeah, I'm seeing the comments. So, I'm glad a lot of people are interacting. So, yeah, I believe everyone by now has his own or her own preferred, like, vibe coding setup or whatever. But we're going to look at this from a high level overview. So, when we speak about vibe coding, especially right now in the vibe coding era, we basically have we can like narrow it down into like somehow 5 different levels. So we have at level 1, which is the chaotic vibe. Basically, just random prompting, and you're just hoping that the model is gonna understand what you want, and whenever something is messed up, you're just fixing it. So you're fixing things as they bring. Okay, this is level 1. I hope no one is level 1, by the way. Then next up we have level 2, which is when we move into assisted coding. This is where basically AI is helping you with the autocomplete, debugging, some code snippets, and just some small tasks. Now, this is good, but it's not as fast as the upcoming ones. We have level 3, which is the structured vibe coding. Here we're basically just using AI, but with more direction. We're planning prompts, we have a clear architecture, constraints, and clearer workflows. And next up we have level 4, which is agentic coding. And here, basically, AI systems start using tools, memory, orchestration, and agents and multi-agents and multi-step reasoning. Now, this is good. I mean, majority of people here might be at level 3 or level 4. I'm hoping no one is at level 1. Now, all of those are good. This is good. You're probably either working with Cursor or Claude, basically. And you might have fiddled a bit with ADK, Google Development Agentic Kit, because they're all high on that agentic coding and such. But today we're gonna be sort of diving into level 5, which is rarely talked about, and today we care about harnessed AI engineering. And this is where we start adding persistent memory, retrieval systems, evaluation loops, graphs, long-term adaptive behavior, a lot of such. And this term is not quite old. It's actually quite new. Claude introduced it later in like couple of months back, and this is exactly where knowledge graphs become useful because we're going to utilize them and they're going to help the agent move from just, generating code to basically understanding context, relationships, decisions, and constraints. So let us first start by defining what harnessed AI engineering is. So we're gonna go back to the uh, very beginning, actually, and I hope that the majority of the audience are familiar with, how did we start with the agentic AI era and when did the shift happen and such. Um, I'm not gonna dive from the the beginning of the beginning. We're just gonna go over it like from a high level perspective, just so that everyone is familiar with it somehow, which would help us proceed in the upcoming slides. So this system, this infographic, or I don't know, we can call it a system, an architecture. This basically sums everything up, and we're gonna tackle it layer by layer before diving into you know the gap and how we're gonna utilize knowledge graphs, just to ensure everyone is somehow familiar, before we kick off. So let us start. At the beginning, we had LLMs. So, everyone was using LLMs and, just writing prompts. This is before tools were introduced. All right. And I'm going to talk about tools in a bit. So, the models were like extremely powerful at pattern recognition. However, they were limited and they didn't automatically know real time facts. They couldn't access APIs by themselves and they weren't able to interact with the outside world. We had, unless you design a system around them, they weren't able. So, like, they were super smart. Think of them as a super smart person, but, blindfolded. No calculator, no phone, no Google, nothing. So, the next step was, introducing tools, and tools give the model action. So, instead of only answering from the eternal knowledge and the data that the model was trained on and such, the model was able to search, calculate, query, run code, access databases, call an API. And this is where we started introducing workflows. Workflows became more useful. So the user asks something, and then the model decides what tool is needed. Then the tool returns a result, and then the model gives back the final answer. This is essentially how tools work. However, tools weren't enough. They definitely are not enough on their own. And this is where agents came in. So an agent added the control logic. It doesn't just, call a tool once and stop. No, this is where we introduced reasoning. And I'm hoping some of you are familiar with, the React architecture. This is when an agent can reason, act, observe, and then, give you the result, plan the next step, and answer. So this is the idea behind frameworks like, React, the agent that keeps moving through a loop until, it reaches a final result. Next up, we have the modern agentic systems, which is what we have now. We obviously need more than just an LLM and a tool. We need memory, prompt templates, evaluation, and sometimes even a human in the loop, or just fully autonomous agents. But like every fully autonomous agent has a human in the loop for sure. And this whole structure is what made the hype right now. So you're probably seeing a lot of content creators, a lot of reels, YouTube, whenever you scroll on TikTok, on Instagram, everyone talking about, oh, I built a Claude prompt template, I built something. So this is the hype right now. And if you recall, when I just started, everyone has his own uh, basically workflow when it comes to vibe coding and such. But like in a nutshell, the key idea here is that a model alone is not an agent, and that you need tools. Tools enable actions, and the control logic, which is what we're using for the agents, enables orchestration. And we definitely need memory. A memory is what enables continuity. Okay? And when we combine all of those together, we get an actual full agentic system. So, better AI systems do not come from only stronger models, they come from better design decisions around them, and the different layers that connect the model to tools, memory, rules, and real world action. So this basically sums up everything that you need to know about, like, where were we and where are we currently. But we do have a gap here, all right? And what is the gap? So, yes, agents are really powerful now. They can write code and all, but there is yet still exists a gap, all right? So, they can write code, fix bugs, search docs, and all, but they often have a lot of problems, and they often struggle with, forgetting what was said before, making different decisions in the same project, maybe repeating the same mistake all over again, or maybe inventing an API, or changing a code um, like they shouldn't touch. Now, you can control that to a certain extent with hooks, but it's not really that flexible. And the more your basically project, like the bigger it gets, the harder it becomes, because an agent needs to remember files, bug decisions, rules, and the overall system. So we're not talking about the model, we're talking about the system surrounding it. So we have a gap here, we have a problem. Sure, there is like some approaches out there, some work to a certain extent, some might not. But this is why Claude decided to introduce harness engineering, and this is where harness engineering basically comes in. So now we're going to be talking about harnessed AI engineering or harness engineering. So I like to think of harness engineering, as if I'm in a race field, and we have Formula One cars and such. Who here is a Formula One fan? Feel free to drop in the YouTube chat box. I myself, I'm not really that much of a fan, but like I do like Formula One races. So I like to think of AI agents like Formula One races because people are usually focusing on the driver only. I mean, some girls only watch Formula One just because they like a certain driver, right? So when you're focusing on the driver in AI, this is the model. So people be asking questions like which model is smarter, which model writes better code, which one hallucinates, yes, but that definitely doesn't win you the race. In Formula One, the driver alone doesn't win the race. There's actually a full entire system behind like those drivers. You have the pit crew, the telemetry, the race strategy, communication system, safety system. So like you have all of those other parts of your system, and you have to work on all of those and ensure everything is properly set up and such. And you have to be a good driver, yeah, but we have a lot of good drivers, and some good drivers often lose, others often win. It all comes back to the system behind them. And this is exactly what a harness is in AI. The model is the driver, and the harness is everything around it that makes it actually, capable of performing properly. So, what the harness does is that it gives the model the memory, the tools, the permissions, the orchestration, context management, evaluation loops, and all. So, instead of you just generating text, it becomes a full operational system. So once again, the driver is the model, the pet crew is the harness, the GPS and telemetry is your memory and context, the race strategy is the orchestration layer, the safety systems are, the permissions and the hooks, and yeah, that's it. We have a Formula One car who's gonna definitely win the race because without his system, he's gonna crash. And this is why a lot of AI agents are crashing at the moment. And this is why some agents might do good, others not, etc. So I like to look at harness as that. Basically, this equation sums everything up. So we have an agent, which is the model and the harness. So we're not only just using an agent by itself, uh, some tools, one tool or one hook or something. No, we are harnessing a full AI system around it. And of course, we have the model. So this is, you can think of it, the upgraded definition of an agent if we harness the system around it properly. So we're utilizing, harnessed AI engineering here. All right. So what is an agent harness? It is basically the layer between the LLM and the real world. This is what we've just talked about. So the model generates, and the harness decides what the model can access, change, execute, remember, verify. Recall the Formula One example that we were talking about, right? So let us look at this example. Maybe you can see the picture clearer a bit before starting on with the hands-on part. So let us open the harness a bit, okay? And look at it. If by the way, guys, if anyone has any questions, feel free to drop them in the chat box. All right, I will be answering them and such at the end of the session. Feel free to drop in your questions. So here we're looking at modern AI agents. Let's start with the center. We have the model. So basically, the model reasons and generate, right? But around it, we have the actual system making the agent useful. So we have perhaps context injection. This controls what information enters the model. The memory keeps track of what should persist beyond one prompt and such. We also have the memory we just talked about, where we're gonna be diving and zooming in into this specific part, by the way. We also have tools and MCPs, and they connect the agents to APIs, web tools, and external systems. We also have file system and Git, and this usually gives the agent durable state, project history, snapshots, etc. We also have permissions and hooks, and this decides like what's safe, what needs approval, what should be blocked, what should not be accessed. And of course, we have the execution environment we're in. This is where the code is gonna actually run. And we have orchestration deciding the flow, what happens next, and when to reset or route tasks. And last but not least, which is often overlooked, is the evaluation. So the evaluation checks if the output is actually correct and such. So the idea here is, yeah, the model is important, but the system around it is what turns it into the upgraded definition of what an agent is, because not everyone is, utilizing this architecture yet, I would say. So, if you're still confused what harnessing an agent is, or what is an agent harness, or what is basically harnessed AI engineering, this diagram basically, sums it up and such. And we're gonna be moving into one specific part, which is the memory. Now, if you already follow me and keep up with me on LinkedIn, then you've guessed it right. For sure, you know that I'm a huge knowledge graphs fan, and I've actually did my two master's theses about knowledge graphs. So this is what we're gonna be diving into, and we're gonna be going through a small hands-on example using Neo4j Sandbox. No need to install anything. I'm gonna walk you through it. So let us start by talking a bit about what a memory is. So a memory is not just chat history, for sure. For agents to function properly and be like optimized and such, the memory needs to be persistent, structured, retrievable, connected, updatable, verifiable, and such. And without memory, the agent only reacts. But with memory, the agent reacts and reasons with context. This is why, let's go back to the earlier slide here. This is why I said that this is the upgraded example of what an agent is, because not everyone is still, following that architecture yet. All right. So the bottom line here is to build better agents, we need better memory structures, and this is what we're gonna be doing. So, what do we need for that? That's definitely a textbook example of a use case where we might utilize knowledge graphs. And knowledge graphs here are extremely powerful because usually graph doesn't just store information, they store the relationships between them. All right. So let us dive into what a knowledge graph is. But before that, this is what we've talked about. Memory is not just chat history, it's also decisions, files, constraints, user preferences, tools, evaluation, etc. Now, all of those can be modeled in a certain way, but the relationships between all of those, it's gonna become messy if we're just gonna keep on writing the instructions in .md files, or building hooks or creating hooks. We need something that's powerful enough, something that allows us to utilize the relationships between all of those, let's say, scattered data points, for instance. All right. So this is where knowledge graphs come in uh, to the rescue. All right. And why knowledge graphs? Because uh, traditional memory systems are not that powerful. And we've seen this a lot, and there has been an ongoing hype around graphs and graph memory and such because traditional memory is failing us. We need, an enhanced memory layer that allows us to see the reasoning paths, the relationships, etc. And this is where the graph memory comes in. All right. So, in a traditional memory system, you basically have just scattered chunks of information, a summary here, a conversation there, a retrieved paragraph, etc. And basically, the problem is that the relationship between those pieces is often lost. We care a lot about relationship because this is a huge issue for agents. If we don't have relationships, then it's gonna get messy. They don't need information only, but also connected information. And this is often modeled as relationships in, graph memory. So instead of us storing memory as, disconnected chunks, we basically store an entity, a relationship, and the reasoning path between those entities, those tiny circles that you're seeing, which are basically, the nodes here. So when we do that, the agent can understand what is connected to what caused what depends on what, and what should be retrieved together. So, for example, a bug can connect to a file, and that file can maybe connect to a feature. And that feature you have can connect to basically previous decisions, constraints, or any pre evaluation rules that you have, basically. All right. And basically, we need retrieval here. So instead of just looking at semantic similarity, which is good, but we need better, obviously, the agent can now actually, navigate context and such. So this is why knowledge graphs are becoming increasingly important in memory-driven systems and even graph RAG architectures. Now, this might be a lot to take in on some. Again, guys, if anyone has any questions, feel free to drop in your answers in the chat box. All right. Yeah, it's definitely a lot to take in. But when you look at it, it's actually really, fun to look at. Like, we're not just typing prompts, we're not just, okay, building a tool, building a hook or something. No, we're actually harnessing a full system around the model. And we're using knowledge graphs to model the relationships between different nodes and such, right? So we're gonna basically uh, we go over the points, all right? Just like a mini wrap up before moving into the hands-on part, all right? So we've looked about both harnessness and memory, and we've you know uh, we've moved from just thinking about AI as a simple prompting tool into thinking of AI as a system and an actual modern system. All right. So let us just quickly connect everything together before we move in into the hands-on part. So what happened recently, or what changed in AI recently, is that we moved from simple prompting into full agentic systems. Now, this is easy to grasp. Most people are familiar with that, and most people are, utilizing agents and working with agentic systems. I mean, there's a lot of new job opportunities when it comes to like that field. And then later on, what happened is once agents became more autonomous, they started needing more than just a model. They need memory, tools, permission, layers, orchestration, etc. So, this is where we are now. This is the modern agents and what they require. All right. And basically, the entire surrounding system is what we call the harness. All right. A model alone is not an agent. The harness makes the model operational, and then add on top of that memory. So the memory here changes everything. All right. And memory is not just the chat history, but also the project context, the bugs, the files, the constraints, the relationship, the decisions, etc. And we emphasized a lot on relationships and the importance of relationships. And once we have a connected memory instead of just scattered and isolated memory, we will have extremely powerful and useful systems. And this is where knowledge graphs come into the play because, they help structure memory into more connected context. And this way, the agents can reason over, and we can basically shift from just reactive agents with no direction into proper, basically harnessed AI systems. So this is in a nutshell what we're looking at. All right, and we're gonna be moving into the hands-on part of the session. So we're gonna be moving into the hands-on part of the session. And what I would like is, if you're joining from your laptop, feel free to just open up a new tab. I'm gonna be sending the link in the YouTube chat box. Just follow along, follow the instructions. Just to set up the environment. No need to install anything. We're gonna work fully in the browser. You don't have to install anything. So this is the link of a we're gonna be creating a Neo4j sandbox, and we're gonna be working with that. What you're gonna basically need is just a Neo4j sandbox. We're gonna be writing Cipher query language, and we're just gonna be modeling sort of graph-based memory structures to basically simulate bugs, files, decisions, tools, constraints, etc. Now, for those of you that are not familiar with what Neo4j is I talk a lot about Neo4j and such. I'm gonna be sharing a couple of resources or perhaps my socials so you could stay up to date on those and such. And if you're not familiar with Cipher query language, also no worries. We're gonna be doing a webinar sometime real soon about that. We'll be sharing details later on, of course. But Neo4j is essentially a graph database. And we've been talking about graphs. So now, of course, you know that instead of just storing data in tables and such, like not traditional data storage, but storing it in a graph format, nodes and relationships and such. So Neo4j here basically thinks in connections, and it is extremely powerful for knowledge graphs, recommendation systems, fraud detection, and even agent memory systems. And the reason why we're working with, you can work locally and such, but the reason why we're working directly on these sandbox is because basically Neo4j offers you a free cloud environment. So this is like the sandbox version of it, and it's completely free. And you can experiment in the browser without installing anything locally. So it is literally easier than ever to get into graphs and to fiddle with Neo4j for someone who's a complete beginner. So you can interact with Neo4j, and you can write Cipher, and you can query and such, and it is all pretty straightforward and such. No need to complicate anything. All right. So after that, you're just gonna click on the create a new sandbox, and make sure you're basically selecting a blank sandbox. Um, you can create up to one blank sandbox, and it usually gets terminated within 3 days, but you can extend it to like up to 7 days. And on the free tier, I believe it's only one sandbox that you can create. Make sure that you're selecting the blank sandbox, not the one with graph data science. We're not gonna be working with any pre-installed or pre-uploaded data set or anything. We're gonna be building our own just to simulate the concept and such. So you should be seeing, after clicking on that, you should see the screen. All right. It should take you to this dashboard, and you're going to have to wait a couple of minutes. Usually takes some time just, to get loaded and all. So give it a while. And next up, we're at step 3. uh, they're gonna basically, when it gets loaded, all right, when the blank sandbox environment gets launched and configured and loaded and all, you're gonna notice that there's gonna be a txt file that's gonna be installed. This is where your credentials are. They basically give you a username and a password, and make sure to keep those because you're gonna need them to connect. All right. So this is step 3. Step 4, you're gonna click on open, obviously, and you might need to give it a couple of minutes before actually, you know, loading anything. Then you're gonna have this pop-up browser, and this is where you're gonna write the username here under the database user and also the password. It is all in the credentials.txt file that was installed. And just click on connect and wait a couple of minutes, around 1 to 2 minutes, sometimes less. I mean, depending where are you joining from. For those joining from Lebanon, I'd say wait a couple of minutes, maybe like two or three. All right. And you should end up with this screen basically. You know, uh, this is where we're gonna be writing the cipher and we're gonna be querying and all. So I'm gonna wait couple of minutes. I'd say just to give you guys couple of seconds to load that up and such. Um, we'll resume in like 1 minute, just so that everyone is set up. Feel free to drop in the chat box whenever you're done and such, so that we can start basically building. Who is done yet? Feel free to drop in a comment. All right, I'm gonna give it a couple of more seconds. All right, awesome. So I'm seeing a lot of people. All right, no worries. Let us start. So this is where the magic is gonna happen. So we're basically gonna let the magic begin. So this is the screen that you should end up with. So Stark is saying almost. Are you done? All right, so we are inside the Neo4j browser here, and this is basically the interface that we're gonna use to create and explore our graph. All right, so at the top, we basically have um, the cipher, basically a query bar, and this is where we're going to be writing our commands using Cipher language, which is Neo4j's query language. And on the side here, you can even save some ciphers here. You can see the history. Can use some cipher reference for those of you that are not good at memorizing syntax or something, or for those of you that are not familiar with cipher syntax. This can be very helpful. We also have here parameters if we want to add those, and here we have some just settings and such. All right, and this is the database information. This represents the nodes. This represents the relationships, and this is basically the property keys. This is how they're gonna look. All right. So usually before starting, it is basically preferred to clear the database or whatever. So we're gonna start by writing a query to do just that, and I'm gonna be basically writing the queries step by step, and creating our memory graph step by step. If you're not able to follow up and such, don't worry about that. I've created a blog that has the full basically the full ciphers and the step by step guide. We'll be dropping it in the chat box as well, but try your best to keep up with me and such. All right, so I've just dropped the link here in the chat box. If at some point you got stuck, or you missed writing cipher query or something, you can always go back to them. By the way, if you like technical blogs and such, make sure to subscribe and follow me on Substack. I basically write weekly blogs every Sunday. So if you're interested in reading blogs and you enjoy reading technical blogs, make sure to subscribe and follow. All right. So now we're gonna start with our first query, okay, which is basically just to delete anything clearing the database before startup and all. So you basically write the query here, and you click on this button to run the query. So just in case there is anything or something, this query basically says, find everything and, just delete it. All right. Now, for the syntax, for those of you not familiar, I'm just gonna start a bit by talking a bit about the syntax, and then we're gonna basically move from that because that's not the emphasis of the session. The match here, it means to find or search for something inside the graph. And the n here, it represents a node. The n is basically just a variable name. You can technically call it anything. So it just looks at all nodes in the graph, if there is a graph. And then what it does is we have the detach, we have the detach delete. So what this basically does is, just delete the nodes and also remove their relationships first. So before deleting any node, you have to, remove their relationships and then you delete them because in graph databases nodes are usually connected and you cannot delete any connected node unless the relationships between those nodes are removed too. So we remove the relationships first and then we delete the node. And this command basically wipes the graph clean, and this is extremely important, before starting with fresh experiments or demos or anything. All right. Now we're gonna create the actual memory entities for our agent system. So first of all, okay, we're gonna start by writing create. All right. Now, uh, what create means is we're aiming to create either a new node or a relationship inside the graph. So we want to create a graph. All right. What shall we do? We should create, all right, either a node or a relationship inside that graph. Now, so for the demo, uh, example and such, I'm gonna start by just modeling how we can create one node, and then since there are a lot and we have a lot of nodes and a lot of relationships, um, I'm gonna just paste that, and you can follow up with me in the blog and paste that as well. We have over 100 relationships in this mini demo. So what I'm gonna do is we wrote the create to create that, and then we put them in brackets, all right, and each bracket separated by a comma and such. The feature is the node here because our node is basically the features, and here we're giving it a name. So we have a lot of nodes, as you can see. All right. You can follow up with me step by step and just copy paste them from the blog, just for the purpose of time and such. And what we have is F1. So what is F1 here? This is basically just the variable name. It can be anything. Again, it can be anything. And then we have the dot, the two dots feature actually, as you can see here. All right. So this is actually the label. All right. And basically, you can think of it as if, like, we're categorizing something or just, writing the type or something. So our node here that we've just created belongs to the category feature. All right. So we've categorized that node. We're going to have a lot of nodes, and each node is going to belong to a different category. All right. So, all right, this node belongs to the category feature. And then inside the curly brackets here that you're seeing, we have this is where the properties go, all right? And here we have the name property. Of course, there is more properties, but again, that would require you to be a bit familiar with Cypher. We're gonna dive into Cypher like in more depth and detail in another session or a workshop. But properties are basically the data stored inside any node. So you have a node, okay, and you store properties inside that node. And it is very similar to attributes in objects, by the way. All right. So right now, our node has a type. It's categorized under feature. It has basically a property called name. All right. And that name has a value, and that value is hybrid retrieval. All right. Same thing for F2, F3, etc. All right. And we keep on repeating this pattern to many different entities of our simulated AI agent memory system. For example, we might have, features, files, bugs, decisions, constraints, etc. As you can see, just gonna scroll over them. Here we have files, here we have bugs, decisions, constraints, etc. All right. And right now, we've only created nodes, and the nodes are isolated, by the way. We just created the information. All right. So after that, we're gonna just run that. All right. And you should see created 28 nodes, set 28 properties, added 28 labels. This means that your query basically ran properly. All right. All right. Now, next up, what we're gonna do is we're gonna connect them. We need to connect those, right? So we're gonna be basically using the match and create cipher for that. So once again, if you're having a hard time following up, make sure to just copy them. So what we have is we're gonna be working with the match, all right? We're gonna be writing the match query as well as the create query, all right? And we're gonna run those up. So what this essentially does, I'm gonna be diving into this in a detailed manner for sure, but what this essentially does is that it creates the relationship among the nodes and such. And as you can see, created 100 relationships successfully. And this is just some extra detail you can dive into, the Cartesian product of them and such. But that's a topic for another day. Let us look at the syntax actually. So we have the match keyword and the create. Now create, we've seen that, but the match is quite new. Is everyone able to follow up? Is everyone following up? If at some point anything is unclear, feel free to interrupt me, guys. All right. All right, I'm gonna take this as a yes. So we've created the nodes. They're separate. Now we need to connect them. This is where match comes in. So what we're doing is with the match query is we're finding the nodes that already exists, okay? Any node that already exists and such. And we're gonna basically, model the relationships between them. So essentially, what we're doing is, okay, look for that has hybrid retrieval, find the file called retrieval pipeline.py, etc. So we're just looking for those, all right? As you can see, all of those that we've created earlier, we're looking for them. We're looking for those nodes, all right? And then after we find them, very easy. I mean, can you build something without finding the tools or the components that you need for something to be built? Of course not. You need to look for those. You need to assemble them, put them in one place, and then to connect them, you start connecting them. So this is where the create comes in, all right? So the create is pretty easy. You're just creating the relationships between them, and it is very straightforward, extremely straightforward. So this relationship here, this is the implemented in, this is the found in, this is the caused by, this is the uses relationship, this is the creates constraints, this is the validates relationship. All right. So once again, if anyone has any questions, feel free to just drop them. All right. And the parentheses here, the F1 and the file one, etc., those are the nodes that we've built. And how we write the relationship is we put them in square brackets, as you can see. So the implemented in is in square brackets. And you even specify the direction. So as we've done here, this arrow basically means the direction of the relationship. So basically, we can read this in simple English. The feature implemented in file. All right. So it's pretty straightforward, very easy to read. We have the arrow, we have the node. The arrow shows direction. The relationship is in the square brackets and such. And what we're doing here is we're not just storing data. No, we're creating the meaning behind the data. And this is often the key idea behind, knowledge graphs. We don't have like separate file or anything. We basically are have building the nodes. We have nodes and we have the relationships between them. And because the nodes are connected now, the agent can understand the context. So it basically knows that, okay, which bug uh, affects which feature. There might be a bug in a certain feature and a bug in another feature, or maybe two bugs in that feature and one common bug with that feature, something. So this is how the disconnected information is becoming the connected memory. All right. Now we're gonna be writing the match query once again. If you've noticed, the queries are pretty straightforward. Like we're just writing create, match, and they're not a lot to basically grasp or memorize. I mean, with practice, you're gonna just basically be more like familiar with cipher queries. Of course, there are some couple of advanced cipher queries out there, but for the purpose of this session, we're not complicating anything, so you don't need to worry about that. All right. So our query is gonna be the match and then we're gonna return them. So if you recall, oh, now we're seeing graphs. So we're gonna dive into that in a sec. So the match, if you recall, as we've talked, it means find or search or look for. And we have the N, the R, and the M. It basically means the N means the node, the R is the relationship, and the M is the ending node here. All right, so we have a node N, all right, this, and we have a node M. M is the ending node, this is the starting node, and this is the relationship between them, and the direction is heading to M, which is the ending node. Okay, you can, by the way, zoom in and click on like the nodes, read the information about them, click on the relationship, see the relationship details, etc. um, Feel free to fiddle with that on your own and such. All right. But as you can see, we can now visualize nodes and their relationships. Okay, I believe everyone is able to follow up. Feel free to drop in the chat box, guys, if anyone is facing any issues, following up, or anything. So we've built our graphs, we have the nodes, we have the relationships. Now we're gonna query, all right? So this is where the harness query will come in, all right? Is everyone able to follow up? I'm reading your comments, guys. I'm glad that everyone is enjoying this session. We're almost done, almost wrapping up. All right, so let us start with writing our first query. All right, so the first query that I'm gonna run is basically, let's say we wanna we want an agent that retrieves context before fixing a certain bug. All right, so how we're gonna do that? If you've noticed, I said retrieve. This is when you know you need to use the match keyword. All right. So again, if you're basically not able to follow up with me, I'm not even typing so fast. I'm just pasting them and such. If you're not able to follow up, you can find them in the blog. Just for the sake of time, we're gonna be like, going over them and such. And if we had couple of extra time at the end, we can dive into some, extra and other queries. So of course, we need to use the match keyword here. Now, what this does essentially is it retrieves, the related features, the related decision, the tools, the constraints, the files, etc. So think of this as if, the harness is assembling all of the context before the model generates a fix. So you'd be just typing a prompt, and your system behind the scene is assembling all of the needed context before you generating a fix. And all of that is from your prompt, basically. All right. So we have the match path. The path is through the graph, and the path is, a chain of connected relationships here. So here, what we're saying is, I want you to start from the specific bug node, all right? As you can see, this one over here. And this over here basically means that I want you to traverse the relationships between 1 and 4 hops away. Now, what do we mean by hops? A hop basically means just, hopping. You're hopping. You're moving from one node into another through a relationship. So, usually, Neo4j will explore nearby connected context around this bug. And finally, we have X over here, as you can see. The X means like whatever you find, just retrieve. Retrieve whatever connected nodes like are found. And then you're gonna, return the path. So you're gonna show the full connected paths visually. And it is extremely important because we're just not randomly searching the memory anymore. No, we are assembling all of the context before our model needs to act. So we have like one bug, and the agent can now, retrieve the related files, the features, etc. And you can zoom in and a bit and dive into those. As you can see, we have 48 relationships and 11 nodes. So this is all from one bug, basically, and what affects who and what is caused by what, etc. All right. Now, this is a great query example. We're navigating the reasoning paths here. Let us take, this is basically just assembling the context. Let us take another example. So if you don't have a harnessed AI engineering system, we would just, go and type a prompt. So there is a bug in file X. I want you to go and fix that. Just that. That's bad. With harness, what we do is, okay, I have a task at hand. The task is I need to fix this. So the retrieved context would be, okay, what is it? What is the issue? The bug. I retrieved the bug. I saw all of the prior decisions, etc., the related tools, the constraints there, etc. All right, so this is extremely helpful for us, like before acting on such. All right, now we're gonna basically try another query. All right. Once again, if anyone is having hard time following up, just feel free to drop in your questions in the chat box. All right. So I'm gonna write this other query, and of course, we had to write match path here. And once again, what we're doing is, or what we're saying is, this query, by the way, is very similar to the previous one, but here we're starting with the feature instead of the bug. So here we have, for example, in our system, the hybrid retrieval feature. All right. So as you can see, the feature, okay, it's called the hybrid retrieval feature. All right. And we're starting from here, and then we're saying, I want you to traverse the connected relationships between like 1 and 3 hops away. All right. So here we're traversing between 1 and 3 hops away. And then finally, all right, we are returning the path, basically. All right. So we're just showing all of the paths visually and such. So here we're not only retrieving information based on semantic similarity, we're basically retrieving the implementation context. So we're not starting from the bug, we're starting from the feature. And from there on, our agent can discover the related files, the tools being used, memory entries, constraints, or any bug related to that specific feature we're starting from. All right. And usually, when you're working in a real engineering system, basically developers like debug and build, we're not thinking in isolation. No, we're looking at the full picture, starting from the feature to know what went wrong, what is causing it, etc. What if I change something in this feature? Which files are going to be affected? What's going to fail? Which tools are related? What are the previous decisions that I did? what decisions exist, what constraints should I follow, etc. So you can already see the picture why this is much better than just typing a prompt. I mean, okay, we're typing a prompt. We don't know if the tool, the coding assistant tool we're using, is basically doing that behind the scenes or not. Or even if we built our own agent to do that, uh, the complex the code base is gonna get, the harder it's gonna get, and it might even start hallucinating or fabricating stuff at a certain point. All right. So we are retrieving the implementation context here, and it is extremely crucial. So, as you can see, modern AI systems have moved from just prompting, to response, and we've moved toward retrieval, memory, constraints, evaluation, orchestration, etc. We've moved into harnessing the system, basically. All right? And this is basically the uh, topic of today's workshop, and I'm hoping um, everyone has enjoyed it. If there's any questions, feel free to drop them in the chat box. If not, I think let's take one more query example and then let us wrap up. So as you can see, graphs are extremely easy to get started with. Now, of course, this is only simulation based example, just to simulate the idea, simulate the concept, but you can easily take this and adapt it into any project that you're working with and such. All right. Let us take uh, let us take one more query, maybe. Let us. Does anyone has like any question? Okay, I believe not. So let us look at. Uh, all right. Let us take this query example and run it. All right. So what this does is we're trying to show the tool routing logic here. All right. So, okay, our agent retrieved the context and all, but what if it's just acting on its own? What if there are certain tools that agent must use here and such? Did it use it and such? Yes, yes, it did. So the agent is not randomly choosing the tools. No, the harness is basically routing the tools based on the context we have about that feature. All right, as you can see here. And you can zoom in, and I believe you can download it as PNG. And yeah, like it's very easy to basically get started with. You can click on the node, click on the relationships, etc. We're gonna be diving into this at a more detail in future webinars and sessions. We'll definitely be diving into Cipher, query, and such. So I believe this wraps up. You can fiddle a lot with tools, but what I would recommend is get familiar with the Cipher syntax first before fiddling with the Cipher queries and such. All right. And you can easily get started. Their documentation is really great and easy to follow up with and such. And I believe this wraps up this session. Let me share my contact info in case anyone has got any question or anything, or if you'd like to stay connected and such. So you can follow me on Substack, all right? And also feel free to connect on LinkedIn and stay tuned for our upcoming webinars and basically events and workshops. Make sure to follow Code Vestira as well to stay up to date and such. If anyone has any questions, feel free to drop them in the YouTube chat box. If not, then I believe this wraps up our session, and I'll see you guys very soon.